Okay guys, so in this video we'll be discussing Born-Haber cycles, and in particular we'll be looking at the Born-Haber cycle for sodium chloride. Okay, let me just get my writing device. Okay, so Born-Haber cycle essentially is an energy cycle, and this basically shows the steps that are necessary um, for various processes such as lattice formation, enthalpy of formation, um, bond dissociation, and stuff like that. Now, let's say we have a question where we're asked to calculate the lattice energy for something like sodium chloride. So, sodium chloride, which is a solid under normal conditions, we could consider the lattice formation energy, right, which is an endothermic, which is an exothermic process, sorry, or the lattice dissociation, which is a endothermic process. And if you think about it, the lattice dissociation must be endothermic. It requires energy to dissociate, that is, to break up 1 mole of an ionic lattice into its gaseous ions. That is what lattice dissociation is, and hence that process must be endothermic, whereas the formation, right, is an exothermic process as the gaseous ions lose some of their translational degrees of freedom in coming together to form this unit. All right, and so that's the formation is exothermic. So I'll just put here gaseous sodium ion. All right, this is a A, by the way. uh, Chloride, gaseous ions coming together to form solid sodium chloride, or the solid sodium chloride could break apart to give you your gaseous individual ions. Now, in terms of the formation enthalpy change for sodium chloride, all right, this one involves basically the formation of 1 mole of sodium chloride from its elements in their reference states. Now, sodium is generally a solid metal at room temperature. Chlorine exists as a diatomic gas at room temperature. Now, only 1 mole of sodium chloride can be formed. Hence, it's called formation. If more than 1 mole is formed, then you cannot use the word formation. You'll have to talk about enthalpy of reaction. So I'll put a half here to balance the whole thing. Okay. Now I have a downward pointing arrow for the formation, because if you look up here at our data, here it is, this one, you realize the value is negative. Okay. And that indicates, well, it's an exothermic process based on that value. And so I have my arrow pointing down. So I can put here formation. You could put the F between the delta and the HR in front. Not a big deal. 411, and that's let's put kilojoules per mole. All right, kilojoules per mole. Uh, the next thing I would probably think of doing is probably to convert the chlorine molecules into individual atoms. Now, if you're going to break bonds, um, that is an endothermic process. You can point the arrow up and we can look at the data. It can tell, here it is, breaking chlorine bonds. It's an endothermic process. Uh, so here we go. And this will give us gaseous chlorine atoms. Okay, sodium, solid, of course. Now, I have the arrow pointing up because the endothermic process. And I will have to multiply that value by 0.5, right? I'll have to cut it in half because we're looking at the dissociation of half a mole, right? 0.5 moles of chlorine bonds. Remember, the bond dissociation energy is really the energy required to break 1 mole of a certain type of bonds. But we are not breaking 1 mole, we are breaking 0.5 moles. So I have to say 0.5, which is a half, times the the delta H for dissociation. All right, I'll just put delta H dissociation just so we don't get a little messy on the diagram. All right, we don't get too messy and you can't see. All right, so I'll just put this. The value is here. We will take up the value when we are ready. All right, so we have gaseous atoms now. Now, I think what we need to do, or what we could do at this point, is convert the sodium solid into sodium ions. Well, convert to gas first, gaseous sodium first. All right, can't convert it to ions yet unless it's in the gas phase. So we could use you could use atomization or you could use sublimation. And we have the sublimation energy for sodium, so we'll work with that. Okay, so now up here we'll have gaseous sodium atoms and chlorine atoms. So this is delta H sub, or you could, as I say, you could put the SUB, the sub, between the delta and the H, or, on the right hand side of it. It's really not a big deal. All right. The next thing we'll do, we could convert the sodium, gaseous sodium atoms to ions, and this is called ionization. Basically, what we'll be doing is to pull an electron off the sodium, the gaseous sodium atoms. Of course, that will be an endothermic process because you're pulling an electron off. You're breaking the electron free from the force of attraction between the nucleus. And of course, that requires energy, right? It's like pulling two magnets apart. It takes energy. It won't happen easily. So it's an endothermic process, as you can see here. All right, you see the value is positive. I put delta H ion. Okay, diagram looking a little ugly, but anyway. Gas, yes, plus an electron, the electron that we just took off, plus the chlorine gas, atoms. The next thing we could do is to do our electron affinity, basically converting the chlorine, gaseous chlorine atoms to chloride ions. Okay, that's what we'll do now. And as you can see, that is an exothermic process. And if you think about it, you're basically forming an attachment. You're forming this interaction between an electron, which is a negative body, and the nucleus of the chlorine atom to give you chloride gaseous ions. Why is this negative? If we look more at a fundamental level, the chlorine atom would have lost some of its translational degrees of freedom, as would the electron when both of them come together. So the electron will have 3 degrees of translational freedom. That is able to move along the x, along the y, along the z by itself. Same thing for the chlorine atom. But when they come together now, they now exist as a single unit. And so the translational degrees of freedom would count for both of them. So there's a loss of translational degrees of freedom, hence the value is negative. Okay, so affinity, negative, arrow pointing down. All right, just put the symbol here. Okay, now delta H, this is this here, we should remove this. Delta H lattice energy, L, or sometimes symbolized by U. All right, a lot of times it's symbolized by U, is what we want to find. Okay, now what we're saying now, to find U, all you have to do is remember this. Just remember that the enthalpy change of formation is equal to the sum of all the other enthalpy changes. All right. What do we mean by this? Well, let's see. Delta H F is equal to, where do I start? Let's say 0.5 times delta H dissociation plus um, delta H sublimation plus delta H um, ionization plus and delta H affinity plus delta H lattice energy. Same thing they sometimes refer to as U. All right. And all you have to do is to substitute in the values. All you have to do is to substitute in the values. Now, let's see if we can substitute in those values. Let's see if we can substitute in those values. Let's see. Let's just clear some space here and see what will happen. Erase some of these and see. All right, there we go. All right, so formation, we have the formation energy. What is that again? What is the formation energy? Oh, here it is. Minus 411. All right, okay. I'm just going to put the raw numbers. Then this one is 0.5. This one is the dissociation, and we are dissociating half a mole of chlorine. So 0.5 times this 243. All right. I'm just putting the raw numbers for convenience and for space. The next one we say is the sublimation. Sublimation is 107.3 plus ionization of sodium 495.8 plus affinity minus 348.6 plus what's the next one now? Oh, this is unknown. This is the unknown. So I'm just going to put delta H L lattice energy RU. Alright. And then I'm going to try to see if I could work with these values. So 0.5 times 243 S plus 107.3 and plus 495.8 plus minus 348.6. Yes. And I guess now I'm at the unknown. Okay. 411 is equal to 376 plus delta HL U. All right. So I'm just going to rearrange a bit. See if I can get this value. 376. I'm going to take this one across the equal sign. So it becomes positive basically. Right? And so HL U, yes. Let's see what I get. 376, right? Plus 411. I look, seems here I have 787, all right? And the values are in kilojoules, so it's kilojoules per mole, all right? And so the value is positive, which tells you that we're dealing with lattice. This is the lattice dissociation energy. Lattice formation energy would be the same magnitude, but opposite sign, okay? And that is how we construct a Born-Haber cycle for sodium chloride and also to make use of this Born-Haber cycle in calculating the lattice energy. Now, you could be asked to calculate any of the missing energy values, but in this case, we chose to calculate the lattice energy. All right. Okay, guys, just review that one and follow the steps, and you will be fine.